Okay, everybody turned it in? So Crystal, let's say, where's Crystal? Crystal? You're in the market for a new car, well, used car, and why would you not want to get one from up north? Like Minnesota, for example. Why would you not want to buy a used car from up north? All right. No? Oh, it's a good thing for you to know then. Because what? What's wrong with these cars up north? Those used old buggers? They're rusted out, right? If you're going to get a used car, get one from Louisiana. What's wrong with, why are they rusting out, Monica? People just don't take care of their cars up there, or what?
Because the moisture from the snow stays on the vehicle and it like starts to eat away at it.
Well,
Something, I don't know, salt.
has something to do with salt, right? If you washed your, I guess, if you wash your car often up there and get that salt off of it, you'd be okay. It's a chemical reaction between the salt and the iron, and it just ends up rusting. It's kind of like electrochemical, but that's really not what we're focusing on. We're focusing on the problem of the salt being there in the first place. Why the heck do they throw, what's with the salt? Where's the salt coming from? On the roads. Why throw salt on the roads?
Melt the ice.
Melt the ice. You live up, I don't know, you live in Minneapolis. Your granny lives next to you, right? And it just, maybe it's some freezing rain, because the snow you can walk on and not slip. But that freezing rain, you get up at 5 a.m., you throw some ice out there on her steps. Sorry, you throw some salt out there on the ice on her steps. Yeah, don't, unless you're after her inheritance or something, right? But you throw the salt out there, right? Why? I mean, you can see it in the picture. Look at this region in here. Right? It's melted. Here it's frozen. Ink is running down the drain. Why is it melting? Why? Does anybody know? No. This is what's peculiar. You can Google the boiling point, melting point, freezing point, whatever, all these different solvents, right? Water is one of them, right? You can. But whenever you Google any of these points, freezing points, boiling points, they're always for the pure liquid, or can it be a mixture? Does it matter? It's always for pure. You add something to water, you no longer have water anymore. Its properties are going to be different. Its boiling point is going to change. Its freezing point is going to change. Now, this is what's peculiar, though. If you add, Jacqueline, you don't have to add salt to water or throw salt on the ice. You could throw pretty much anything, and the freezing point is going to go up or down. Jacqueline, right? Where's Jacqueline? Jacqueline, way up here. Oh, my goodness. I got to get my little list out. Jacqueline, what is the freezing point going to go up or down? She's right. Do you see why she's right? Because if the freezing point goes down, it has to be a lot colder to melt, right? So that's why you throw something out on the ice. It really doesn't matter what. Throw something out on the ice. But you might as well throw something that's cheap, right? Sugar would have been a heck of a lot nicer. It's not going to rust out any cars. Look how expensive it would be. And you'd have, I don't know, probably little birdies and things licking the roads. I don't know, right? Wouldn't you? I don't know. But it needs to be something really cheap. And the problem is salt just rusts cars in the end with the chemical reactions. But that's just life because it's so cheap. Okay, so you throw anything, right? You mix any two substances, and the freezing point's always going to go down. Okay. If you take a look at this picture here, just trying to cook some macaroni, And Pamela, you're lucky enough to live in Denver, Colorado. You're going to have to sit there and boil that stuff longer, or will the spaghetti cook quicker in comparison to some dude or dudette in San Antonio? You have to cook it longer. Why? She's right. You got to sit there and cook it longer because it's something to do with atmospheric pressure. The elevation, yeah. The water can't get as hot because it boils sooner. It boils at a lower temperature. It's because of the atmospheric pressure thing. So what she could have done is dump anything in water. Then its boiling point is going to go up. So when you look up the boiling point of a substance and Google it, it's going to be the pure compound. It can't be anything mixed in there. You add anything to water, its boiling point goes up every single time. Okay? So that's just how it is. So she could have done that. And some recipes, I think, you have to really start looking at all these boxes of macaroni. But, so many people are diabetic and there's all the sodium problems. They're not going to tell you to dump in salt. They're not going to tell you to dump in sugar because that's going to mess up the flavor. So, they find some peculiar ways of doing it, I guess. Okay. Now, we're going to have a bunch of equations here to calculate new boiling points and new freezing points. And there's a little technicality. You may not even notice it. But for all these equations to work, whatever we're adding has to be a molecule. It can't be salt. Salt's an ion. Its effect is even 2 times, 4 times, 6 times as big. So there's just a background information for you to know. You really don't. It's not even that important. But what I guess I'm saying is that all these equations work perfectly for sugar. Because it's not an ionic compound. There's no charge. Okay. And the equations are just modified in a very simple manner for ions, but that's okay. We're just going to talk about molecules. Okay. Let's talk about vapor pressure. I've got a beaker of water sitting here, Brad. How do you picture vapor pressure? In your mind, what's going on? What's for vapor pressure? Something's got to be moving around.
Pressure of whatever's happening in the meniscus.
Yeah. The meniscus is talking about that surface, right? That top, and the pressure is whatever happening. What creates the pressure? Yeah. Well, what creates pressure? Gas pressure is created by gas molecules flying around pushing on stuff, right? If you have gas pressure, that's just created by gas molecules flying around, hitting the surface, hitting the container, whatever it is, hitting the pressure gauge, whatever you're measuring the pressure with. And the harder they hit, faster they hit, the more often they hit, right? The higher the pressure. So here's an example of how a good way to imagine vapor pressure, right? There's his meniscus that Brad was talking about, right? That top part. And then you have stuff popping in and popping out. Now all of this is the rates aren't going to be the same of water molecules popping in and popping out if it's not covered, right? Because if it's not covered, it's going to be gone after a while because the rate of popping out is a lot bigger than the rate of popping back in. Evaporation is a lot faster, happens more often than condensation. But if you seal it, if you cap it, you get the rates to be the same, and it'll hang out. But the vapor pressure is just that. The pressure exerted by these little water molecules. That's the vapor pressure of the water. Okay. What's the total pressure? Well, you have to add the pressure of all those gases that are in there, all the air, and you just get atmospheric pressure. Okay, so the vapor pressure is just the vapor pressure exerted by the water molecules. And what they're trying to say is, what does this have to do with boiling? What does vapor pressure have to do with boiling? Do you remember? We talked about this very briefly. You heat this thing up, heat this beaker up, what happens to the motion of all this stuff? It goes faster. Will I have more in the vapor phase? Yeah, most definitely. Everything's going faster. Of more in the vapor phase. Heat it up even more. Things move even faster, even more in the vapor phase. Until finally, I can only heat it up to a certain point. Then everything wants to be in the vapor phase. That's called the B word, boiling, right? Once everything wants to be in the vapor phase. So once the vapor pressure is the same as the external pressure, it boils. So that's why they're talking about vapor pressure here, because we're supposed to be talking about, oh, the boiling point's going up all the time when you dump stuff in there. How much does it go up? Well, it really depends. It's all pictured on this vapor pressure. Why does it happen? They're trying to, here's the picture of it, right? Typical vapor pressure. And then you have these blobs floating around in there, right? Here's whatever we dissolve, the blue balls and the green balls in there. That's our solute. They're trying to say that it's blocking. The water can't get into that vapor phase. So if it's blocking it, the water can't, vaporize. Would the vapor pressure be lowered or raised if you dump some stuff in there? It's blocking it. It's preventing water molecules from getting into the vapor phase. So there's not going to be as many of them. There's not going to be as many of them flying around and hitting the surfaces and things. So the vapor pressure should go down, right? Because there's not as many gas molecules anymore. So if the vapor pressure goes down, well, then you're already starting way down here somewhere. You have to heat things up even more to get it to boil. So you're going to go beyond 100 degrees Celsius. You're going to go, at this pressure, because it boils at 100 degrees Celsius at 1 atmosphere on our bench. So if you dump some salt in, it's not going to boil at 100 anymore. It's going to probably boil at 105, 103. Depends on how much salt you dump in. Okay, because of this blocking of the solute molecules. Okay. So that was this. Does changing the amount of pure water change its vapor pressure? And how do we determine the vapor pressure of pure solvents? Well, did it matter how much water you have? Do you always have the same vapor pressure? Yeah, got to keep the temperatures the same. Yeah. Yeah, you do. It doesn't. The amount of water doesn't. It's like saying if it did, you'd have to have different tables of boiling points for different amounts of water. So that doesn't happen. But the amount of water doesn't matter. No. How do you determine the vapor pressure of pure solvents? Google it. Or look in tables, right? You don't have to memorize that stuff. You just Google it. But how do you get the vapor pressure of solutes? Now you have to. How do you get the vapor pressure of mixtures, of solutions? Now you have to do some calculating. Okay. There's 3 colligative properties of a solution when a solute is added to a solvent. So they're going to use big B's for solute, solvent big A. There's little subscripts to help you keep track of stuff. Oh, let's back up though, Angelica. What is colligative? A colligative property is, yeah, you add something to a solvent. Well, it may not be a colligative property though. Is density a colligative property? There was intensive properties and colligative properties. Remember? Intensive just meant the amount didn't matter. Colligative meant dump more stuff in, the property changes even more. So what we're talking about would be colligative properties. The more stuff you dump in, the more the boiling point goes up. Okay? And the more stuff you dump in, the more the freezing point drops. So the first calculation, so there's 3 colligative properties. The properties we're talking about are vapor pressure, what's coming up, boiling point, and freezing point. So we're going to have an equation for each one of those. So how do you get the vapor pressure of a solution? How do you get the boiling point of a solution? How do you get the freezing point of a solution? Because if it's pure, you just Google it. But if it's not pure, you have to calculate it. So let's take a look at vapor pressure first. Now first, here's the equation for vapor pressure. We have to know how to use it. We're going to calculate a delta P. But when we finally get that number, that delta P, Brittany, our vapor pressure is going to go up or down by delta P. It goes up. So you have to remember that, right? Because you get a number for this, but you have to realize, oh, it goes up. So you have to be adding stuff. Okay. So how do you get this delta P? You take PA0 times XB. Now PA0 is the vapor pressure of the pure solvent. Vapor pressure of the pure solvent. Now there's some tricks that you don't have to memorize, that they're consistent. One of those tricks are whenever they have a little superscript 0 and it's not a degree sign, it means pure. And then the A is the solvent. So pure solvent, P is the vapor pressure, so vapor pressure of the pure solvent. XB, oh, what's XB? It's something with the solute. It is going to be, it's one of these concentration terms. Do you want to know which one it is? It's mole fraction. I wish they would have used, I don't know, some other symbol than X, but I guess X is always mole fraction, so, okay. So that's the mole fraction of the solute. So if you're going to calculate XB, you have to use the mole fraction equation, right? So you take the moles of, well, instead of A, moles of B, right? Mole fraction of B will be the moles of B over the total moles. So you can calculate mole fraction and get a vapor pressure change there. Okay. However, I don't think there's a whole lot of questions on vapor pressure. I think the questions really are on these two. Gloriana, the boiling point for solutions, it goes up or down by delta T? It goes up. So that means to get the new boiling point, we have to add or subtract this delta T. Right? We're going to know what the water usually boils at 100. We get our delta T to be 2.5. So to get our new boiling point, do we add the 2.5 or subtract the 2.5? We add it. So you're going to be adding these delta T's. Right? And here's the equation. I guess the little b stands for boiling. Okay. So we'll calculate this. We'll calculate delta T. All right. We need to plug in our concentration term. The only hint they give you is that little m. So it's going to be which one of these? Molality. Yeah. Here, this one. That is going to be your little cm. Okay, so I'm not going to be telling you that cm is molality. You have to realize it. I guess the only hint is the little m. So the moles of the solute over the kilograms of solvent. Okay. All right. Get the concentration of your solute. Kb, look it up. Look up for water. It's just some constant. They give it some fancy name like ebullioscopic constant, but it's just the boiling point elevation for water constant, Kb.
Will that be given?
Yeah, they have to. If not, you Google it, right?
Like, put on, like,
Oh, I'd have to, yeah. Yeah, I'd have to give you those constants. It's just like the Kf for freezing point. I have to give it to you. But freezing points, they always go what for solutions? They go down. So you go through all this work to get delta T, and you better what? You better subtract. Okay.
So basically with all of these, if it's 12-inch for boiling point and freezing point, you'll give us the kb, and you just have to calculate the cm with the given information in the problem.
Yes.
And then subtract.
There you go. That's Brittany's exactly right. She's the game plan. Do you see the game plan on what's coming up for all this homework? They're going to give you a bunch of data. Let's look at the freezing point one, right? They're going to give you a bunch of data. You have to calculate your molality, your cm. And then you got to look in some table, or they give it to you, this constant Kf, right? And then multiply them and get your delta Tf, right? And then, let's say if it's water, you better subtract whatever you get, that delta T, from the freezing point of water, which is 0 degrees Celsius. So subtract from 0. I think one of the only other place I think you can screw up is if you use, make sure you use the Kf for the freezing melting and use the Kb for the boiling one. And you have to always look these up for the solvent. Water is probably the most common, but they could have ethanol. If they use ethanol, well, make sure you use the Kf and the Kb for ethanol, whatever your solvent is. All right? So again, you look up. Yeah, or a big table. I think it's going to look stuff like, I think I have one here somewhere. Like here's some. Yeah, in the appendix. I think they're almost always listed in the question, but I could be wrong there. Where are we? Okay. Overall, these colligative properties, this is their terminology here, Ashley. Overall, these colligative properties are called vapor pressure, no, it's vapor pressure, right? Because vapor pressure goes down. Because that blocking idea. Vapor pressure lowering. Boiling point, Desiree. Boiling point. Where's Desiree? Boiling point. The boiling points always go up. So it'll be boiling point elevation. Yeah. And freezing point, everybody? Depression. So when they're talking about this stuff, you're going to see the words boiling point, elevation, freezing point, depression. That's just what they call them. Because boiling points always go up for solutions. Freezing points always go down for solutions. Okay. Let's see. So if I remember what I did here. Yeah, I did. Okay. Everything we have so far is right here. Right? We have these definitions for concentrations, and you have these three equations now. All right? So this is what things are going to look like for the quiz. I'll be giving you all this stuff. Okay? But you just have to know how to use it. Okay. A solution was prepared by dissolving 1.258 grams of naphthalene, which is C10H8, and 25 grams of benzene, which is C6H6. What is the freezing point of the solution? I'm giving you a whole bunch of stuff here to make it as complicated as possible. Right? I'm giving you, heck, I'm even giving you stuff on water, and water's not even part of the problem. See that? Because people, for some reason, like to use water all the time. Well, water's not even in here. Right? So don't use the stuff on water. That's a hint. Okay, let's ask Marcus. Where are you going to start on this? Where should we start on this? Yeah, the equation. Which equation, Marcus? The TF. Exactly. Start with the equation. And then pretty much do what he said. Plug and chug. Plug it into the equation. So let's start with that equation here. Delta TF equals KF CM. Okay. Now the idea is they want to know what the freezing point of the solution is. Jalen, just make sure we're all on the same page here. How do we get our final answer? Right? In other words, if you get delta TF, Marcus says delta TF, is that our final answer? It's not. What do you got to do with it? Subtract it from what? Where is it? Subtract it from the normal freezing point, right? And the solvent isn't water, it is... Ooh, how can you tell? Is the solvent naphthalene or is it benzene? And the only reason why is because... Well, yeah, that, but also there's more benzene, bigger number. So the guy with more is always a solvent. So we're going to go through, get our delta TF, just like Jalen was saying and Marcus, right? And then someone recognized, oh, benzene is the solvent. So here's my freezing point, my 5.5. I'm going to take my final answer is going to be 5.5 degrees Celsius minus, I don't know, whatever you get for delta TF, right? That's going to be my final answer. Okay. So Marlena, does that make sense? Make sense? Okay. So, Naya, get us started then on Marcus's equation here. What would you do? Yes, Brittany.
Why didn't you use the 5.065 if it's labeled KFF?
Oh, while I was doing it, I was jumping to the very end.
Okay.
And to get the very final answer, you have to take delta T and subtract it from the regular freezing point. And that's all this is. So I had to look up the freezing point of benzene, which is this number right there.
Okay, but in the equation...
Now the equation doesn't even have the 5.5 in it. All right? So Naya's going to tell us what to do here. Yeah, that's okay. We're going to get it. Naya, what are you going to do? We're after the delta TF. We need to know a KF and we need to know a CM. Does anybody see what to do? Just substitute. Yeah, the KF has to be 5. See, here's where Brittany, here's your 5.065's coming in. 5.065. Okay. And notice we had to pick the 5.065 because our solvent is benzene. All right, so this table's not going to help because it's boiling points and KBs. So don't use him. We have to use benzene and it's KF. Okay. What now? Vante, what now? Yeah. What equation is that? Yeah, it's that little m. He's plugging in this one. He wants moles of solute over the kilograms of solvent. So let's get that little CM. Man, we're probably going to have to do that over here somewhere. Moles. Now, moles of what? Moles of, the formula is? The C, I just want to write the formula. Does anyone see what it is? It's a solute, but what's the formula for it? If you write in what it actually is, it'll be a lot easier. That's the question. Which one is it? Moles of C10H8? Has to be of the solute. See, if you write solute, to me it's not as, if you write this, just copy the equation, I'm not so sure what the next step is. But instead, if you write what the compound is, what is the sign? This one, right?
Yes.
It has to be that C10H8. It's a lot easier. For me, it's easier to see what to do. And then instead of writing solvent, write kilograms of C6H6. Because then it's more in the format of what we've been doing this whole, up to this point. Okay. So Jesus, can you give me one of those? Top or the bottom? Man, yeah, we're going to need a calculator. All right, what are you going to do? What are you going to calculate here? Okay, he wants to get the moles. So you'd start with what? Yeah, how much C10H8? Oh, here, spaced down here. How many grams of that stuff? 1.258. Right, 1.258. Yeah, here it is. Do you see it? So the 1.258 grams of the C10H8. That's right. And let's get that into moles. I need a molar mass of that stuff. Does anyone figure out what the molar mass is of that thing? Is it 128? 128.1? That sounds even better. All right? So it's 10 times carbon plus 8 for the hydrogen, right? So there we'll have our moles. Need some solar power here. There it goes. All right. 1.258 divided by 128.1, about 9.82 times 10 to the negative 3 moles. Okay, so we've got that part. Bianca, how do you get kilograms? How are you going to get the kilograms? All right, we have the moles. All right. How do you get the moles? I'm sorry, not the moles. How do you get the kilograms? Grams of kilograms. How do you get grams of kilograms? 1,000 grams to 1 kilogram. Someone got it. So we've got 25 grams of benzene. And they said there's 1,000 grams for every kilogram. All right, Gloriana, what did you get for kilograms of solvent?
Kilograms of solvent, 0.025.
0.025. All right. So now we've got the top and the bottom. So we are getting close. So for my little cm, my molality, I got about 0.39. Did anybody else get that? Okay, I see some shaking heads, so that should look good. Okay, so we're going to put that number right up here. Yeah, around very close to 2, 1.99 or something, right? Okay. So my final answer is going to be what? How do you get your final answer? Subtract it, right? Because it's always freezing point depression. So you just have to know that. You just have to remember freezing points go down. Otherwise, right, there's no other way. 5.5 minus the, 2 essentially, right? About 3.5. In units? What would be the...
Did you just round up?
Because I don't want to do my calculator.
Oh,
Yeah, but that's either way works. 3.5 units. You don't have those points. Go all through this work, and then what would be the units? It has to be the same units as this one, because you're taking this one minus that one. Celsius. The table's not that great. It should have units in here to help you out, but it'll be Celsius.
Just out of curiosity, where did you get the 5 point? Well, I see that table, but I have a different table in the book that's. Oh, never mind. I found it again.
Okay. All right, now you got several of these. Yep. Okay, so look at the other ones. Now I think the next one looks kind of straightforward. That number 1. I think we should do like 2 or 3. Which one looks more complicated? Let's do the most complicated one.
The last one.
3? Okay, let's do 3. So let's work on number 3. Oh yeah, number 3 is definitely the most complicated one. A 0.0182 gram sample of an unknown substance was dissolved in 2.135 grams of benzene. The molality, which is determined by freezing point depression, was 0.0698, little m. Yeah, they gave us the little molality. What is the molecular mass of the unknown substance? This is done a lot because, like proteins, a lot of those big compounds, knowing molar mass is really helpful. So this is an easy way to do it. It costs you 2 cents. Okay. So let's see if we can get some ideas here. Danielle, where's a possible starting point on something like this? Yeah, that'd be a good place. Might as well, right? Delta TF was KF CM. Okay. But they want to know what? Crystal, they want to know what? This final answer, what do they want to know? They want to know. They want to know what? The molar mass, the molecular weight, right? Is that in the equation? No, not in the equation. But I guess we're going to have to write a new equation. Molecular weight is what over what? What are the units? When you add up all this stuff, what do you always write? Is it moles over grams or grams over moles? It's grams over moles, right? You add up all this stuff, you always get grams over moles. That's an equation. The reason why it's an equation is because if you know, you plug in this number, divide the two, and you'll have molar mass. We already know one of those. Which one do we know? Yeah, it's going to be how many? 0.0182. We already know that one. We already know that one. We just have to get the moles. Okay.
And are we just changing that number into?
Well, we can't because we don't know the molar mass. We have to get the moles. We're going to get the moles from where? The molality equation. Where's our molality equation? Moles of solute over kilograms of solvent. Let's write that. You'll see it. Little m, moles of solute over kilograms of solvent. Now, writing the words solute and solvent I really don't think help a lot, so let's write in what they are. That's really moles of what over kilograms of what? Yeah, moles of the unknown all over kilograms of benzene. And we know the molality. So do you see how to get the moles? Right? We know the molality. So what's this? What's the little m? Everybody, what's he going to be? .0698 is the little m. Right? The kilograms of benzene, what is that one going to be? The kilograms of benzene will be... Yeah, Gloriana knows the trick. You see what she's doing? She's just moving the decimal place how many times? 3, to make it smaller, to convert grams into kilograms. What she's doing is she's just saying 1, 2, 3. And if you're not sure, you can work it out. 2.135 grams, 1,000 grams in a kilogram. But either way, you'll get 0.002135. Okay, so we can solve for the moles, and then we'll put it in. Like I said, they do this a lot to get molar masses of compounds. Right. So we'll solve for. Then substitute. You should get a molecular weight. And don't worry if it's a huge number. Did you get an answer? Oh, what did you get? Yep. Well, that's your moles, and then you have to substitute it in down here, Vante. You got to put it into here and divide it into the grams. Anybody get an answer? For the final answer? Final answer, several folks got 122.13 grams per mole. So if you got somewhere around 122 grams per mole, I think you're doing it right. What did you get for your moles? 1.49 times 10 to the negative 4. Plug in your grams, divide it by the 1.49 times 10 to the negative 4. It should work.
Every time they ask for a molecular mass, you have to use the MWT equations.
Oh,
The UC fraction.
actually, you know, Gloriana's got a good point here. I don't know if you heard her question, but let me rephrase it. Here's what I'm giving you, right? Is there an equation up here with a big M or big MWT, a big molecular weight variable? There isn't, right? So whenever a homework question up to this point right now, if they ever ask you for molar mass, you have to write the equation what over what? Grams over moles, substitute the 2 in. That's your only way to get it right now. Yep, it's a good point. Yeah, divide those 2, and you should get your answer. Okay, so 3-day weekend.